Okay, so this is going to be somewhat of a hands-on talk. I'm Noam Elfanbaum. I work at Bluevine, which is a fintech startup in Israel. I help organize the PyWebIL, the monthly meetup, and the PyCon Israel. It's kind of new, only 3 years. So you're welcome to hop on the next one. And you can find me online at Twitter and at noamelf.com. So, what is a program profile? So a profile is something we do on a program in order to understand what its resource consumption is. And we can use it in production to monitor our service. And we can also use it to debug performance problems that we see just locally when we're working. So in Python, being a battery-included language, has a built-in profiler in the standard library. So it has 2 of them. One is a pure Python implementation, and after it, someone contributed a cProfile, which is just a C extension of the same profiler. It's just faster. So we're gonna start with a demo, which is the easiest way to understand stuff. So we have this module in our production, and someone's noticing it's being kind of slow. What it does power twice on a number it receives. It counts the digits of that number using conversion to string and then length on it. And then it just does the calculation and prints it out. So let's run it live. So we're running profiling demo. So it takes quite some time to run. We're running it locally, we're trying to debug, and it will come up soon. Okay, so it takes 9.1 seconds to run. I'll make the screen a bit larger. Okay. Can you turn off? Raise the bright. Maybe I can do it in white colors. By the way. Let me think if I can fix that. Don't really want to get into changing the color of the terminal, but we'll try work it out like that. I hope you see it well enough. Maybe we can turn off the upfront lights here. Can you add time? Oh, just for the number? We can run. You can see it here. I can highlight it like this. So it took 9.1 seconds to run. So what we're going to do is we're going to run it under the profiler. So we're going to run Python, add the -m to run the module cProfile, and then use -s to sort it by the total time each line of code took to run. So let's run the code again. It will take the same length, but we'll see the results. We'll see what happens. Now, before we see it, what do you guys think? Which part of the program is making it slow? Is it the superpower or the count digits? Who thinks the superpower? Okay, and who thinks it's the count digits? Okay, oh guys, you're good, I must say. I did it in another conference in Israel, and no one, it was a different ratio. So we're gonna see it as well here. So apparently, counting digits is very expensive in Python because we need to convert a very large number into a string. And then actually the length method itself is not so expensive, but the transition into a string is very expensive. And we can see it takes 8 seconds, that's 7. And the superpower, this is the count digit, and the superpower only take 200 milliseconds. So, good job, guys. Let's continue. Now we want to create an optimized version of it. We want to run it much faster. So I've created an optimized version. Do you think, can anyone think what it does differently? Yeah.
Use module operator or divide operator?
Not modulo, something else?
Log function.
Right, exactly. It's the log function. I hope you didn't see when I moved it for a second there. So exactly, just use the log10 function, and then it moved much, much faster. Let's try it now. Took 439 milliseconds, which is much, much better for us. But the output is much bigger, and you just see this very large output because of the imports. Imports is there's a lot of function calls when you do an import. You see a very big output. On the top, you see that the superpower is now the most expensive function. Okay, cool. So, it looks like magic, right? When you look at it, how does Python does that? It's I know it's so nice to have, but when I saw it, I was wondering what are the mechanisms that helps it do it. So Python has pretty easy access to its stack from everywhere you are in the Python execution in your program. You can see the whole stack of how you got there. And so the most profiler, what they do is run as part of your Python process and set up a trigger to capture the stack. And then it can later do the analysis on it. So let's see how we access the process call stack. So we can easily access the stack using the cProfile method. And then we'll just run on it, convert it to something that we can access easily with the tracer module, extract stack, and print it out. So let's run it. Here we have some more functions that help us just to see the hierarchy of the code when we run it. So these stack access. So this is the actual code here, and when we run it, we'll see that the first line is in the module level, and it shows we were calling bar. The second line here is in the bar function, and we're calling the show stack function here, right? And inside the show stack, we see the for loop. So we can really easily, just by doing cProfile, access Python stack. Now we're missing when it will be called, right? We need some trigger to call it. So Python, or in general, profilers have two types of triggers. One is a deterministic trigger, which is then later a deterministic profiler. It's triggered on every function or line call, and then you can see the exact execution path. And we have statistical profiler, which is triggered on a certain time interval. So let's see how someone builds a deterministic profilers. So Python lets you specify the callback that gets run whenever a line or a function is being executed. You can do it using cProfile or cProfile. The difference is the cProfile is calling the handler every time a line or a function is being called, and the setTrace is being called only when a function is called. Now, when it's called, we'll record the stack. So let's see an example of that. Whoopa. Okay, so we're using the cProfile. Here is our handler. The handler receives a call stack argument, an event, and the arg itself. We'll see the output later when we run it. But in general, we'll see that the event is a call to a function. The argument is the function name, and the line is something that we created here. It's just what line it's on. Now we're gonna set the profiler just like that using the sys module, set profile and our handler, and we're gonna call hello world just for fun. We can execute whatever code we want. So let's see how that goes. Okay, so we're going to do Python set profile, and we're going to run it. Now we can see the output. Let's also maybe see the code, so it will be easier to understand. So this is the code, and this is the output. So you see that the first event that was received is a C call. It's a C call because Python print function is actually implemented in C. And we see the line itself, print hello world. Now we get another event, cReturn, which is the function returned, it's finished. So think about when you want to create the timer, you get the time it started, the time it ended. And then you get another event, which is just the return of the whole executable, the whole program. So now we have our deterministic profile. We know how to trigger it, but how do statistical profilers work? So what they do, like we said, they sample the program on a given interval instead of every line call, on an interval that we decide in advance. And one way to implement it, you can implement it in several ways, but one of the ways is to implement it using an OS interrupt or an OS signal. So let's see the code that uses it. So we have our handler, right? It's very similar to the handler we used in our deterministic profiler. The handler is being called, it receives the signal number, which is less interesting for us, and the call stack. We extract the call stack, and then we can print it into screen. In a real profiler, we'll capture the results and for later analysis. Now, this is the interesting part for us. This is how we set the actual signal. So we create a signal, cProf. It's a signal that is used for profiling, actually. And we put the handler on it. So when the signal is called, the handler will fire. And we put a timer on it. So the signal will be, like the OS will send the signal every interval that we put. This is the first interval, and this is all the intervals after it. And we also need to do something else. We need to remove the timer when the program exits. So this is a pretty nice module that Python had that I wasn't familiar with it. It lets you execute something at exit. When the interpreter exits, it will execute this function. It will just set the timer to 0. Now, this is the explanation. It's nice. Okay, so the last part, we're going to call the function that starts the sampler, that sets the trigger and starts the sampler. And then we're going to make our calculation, and we're going to print it to screen. Now let's run it in our terminal. Okay, so this is our code. And let's run it. So now you're going to see something which is pretty interesting, right? We can see that we only get the len str like before. We only get this part of the code being sampled. And I guess you know why it is like that? Right? Since we're doing a statistical sampling, we're not seeing, so the answer was it's just the longest one. So since we're doing a statistical profiling, we don't see everything that is being executed. We're just sampling on a certain interval. So what you get is less intrusive. Like it won't impact performance as much, but you also get less accurate analysis later. So now we know how to do both. So now for the practical question, when do we use which profiler? Someone say? When will we use the statistical one, and when will we use the deterministic one? What are the use cases? Which use cases is better for which interpreter, for which profiler? Mm-hmm. Yes?
I wouldn't use the first profile in production.
You wouldn't use it?
No.
Oh, okay. Good instinct. Okay, cool. Yeah, so that's exactly. So that's a big part of the answer. So the statistical profiler, since it's controllable and predicted, right? You know what the interval you're going to sample, and you know what is the effect on your production system will be. So it's much more suitable for production monitoring. But it's less accurate. So when you debug locally, right, you might want to use the deterministic profiler. It introduces a fixed amount of latency, but you don't really mind when you're doing it locally. Yeah, good instincts. So for the most interesting part of our lecture, we want to build a profiler by our own. So we have all the parts, we just need to merge them together, merge them in. Let's see, okay. So we already know how to set an interval, right? How to set a sampling interval. So we're going to set the signal, set the timer on the signal, and register and remove it once the program exits. Now the sample method itself is a little different now because we want to collect the data, right? So what we're going to do is extract the stack, and then we're going to do a nice trick where we join the stack, right? We join the stack layers into a single string separated by semicolons, and then we count each time we arrived at that path. So we know how many time we spent there. Here we have a global variable, we keep it there. This is a naive profiler, right? So we can do global variables and stuff. And when the program finishes, we can call the format stats and output it in a way which is, we'll use the flame graph tool to show it very nice on screen. And this is its format. It just put the frames with semicolon, like we said, and then the count of how many time we spent there. So let's go back to our command line. Oh, so firstly, I need to prove to you that it's actually 25 lines, right? So we're on 25 lines of code. And I was pretty generous with it can be shorter if you're interested. I was pretty generous with the spaces and stuff like that, so you won't say I'm cheating. You see we have the imports on different lines, right? We have 2 spaces here, so there's a lot more, we can put in a lot more stuff. And let's use it. So in order to use it, I've created a demo program. What the demo program does is a simple calculation. It has 2 functions here. The main function is called the calc function, and it does power. I'm using power all the time because it takes some time for the CPU to execute. So we're doing power 100,000 and then power 200,000. Then we're calling the start method on the profiler. We're calling the code and formatting the stats, printing it to std out. So let's run our code. Okay, so this is the format. I'm not sure if it was clear earlier, so now you can see it more clearly. So we see that we spent time here in this whole stack is where we spent this amount of samplings. Okay, so we've been in main calc when calc was with 200,000 79 times, and we've been in calc 100,000 24 times, which makes sense because it's a larger number, right? So now we can take this code, which is it's pretty clear when we're just using it for a very simple program, but it won't be in a larger program, right? So in order for really reviewing it, we can output it into flame graph. Into flame graph, and then output it into our browser. And now the flame graph tool, I'll give the reference to the guy who invented it later. I really like it. It's a really simple format, and you get really nice output. So it's actually an SVG that shows you a nice diagram of like a relative part of the program where things have been. So we can see that main had 91 samples, right? 100% of the samples. The calc 100,000 had 24% of the samples, and the calc 200,000 had 75% of the samples, which is pretty clear, right? Makes sense for us. So this is a simple program, but if we'll take a more complex one, for example, downloading PEPs into our local hard drive, which is still simple, but complex enough for our lecture, for our talk. So what this program does, it composes a URL, gets to the python.org, and downloads a PEP. Downloads a PEP using URL open, saving it to memory, reading the request, saving it to memory, and then writing it to a temporary file on disk. And the main function, it loops through 4 PEPs in this example, run the save PEP, and says it accomplished it. We're outputting it to std_error because we want to use the pipe for something else. std_out we want to use for something else. And that's it. And now we can call our code, call the start, run the main function, and then print out the stats. So let's see. So like I said earlier, I'm counting on the Wi-Fi here, so it's good. Actually, I'm surprised. I thought I'll have an Ethernet cable. So what we see like we have an output that we can't really understand anything from it. And here comes the flame graph tool to the help. And it will run everything back. But in the end, we receive a very nice diagram, again, that shows how much time each part of the program was sampled, how much, like the count of the samplings. So what we can do, we can really look into the diagram and start like to understand. Actually, it's nice also for just understanding the code if you want to understand like the standard library or stuff like that, to just see the execution path. And if you want to focus on a certain place, for example, we can click on it, and then we'll have everything zoomed out, and we'll only zoom on this certain part and see where it spent its time. Tokenizing stuff, opening them, we won't really get into that. But it's something that you can do with your own code and really get a good notion of where you've spent time. Another nice thing about it, by the way, if we're here already, it works really nicely with grep. So, for example, I can do like a grep on the results and remove something. For example, remove what we can remove. It will be interesting for us. So we can remove any connect, any place we have a connect method. And then we receive a much simpler diagram, right? The diagram will be smaller. It will be kind of funny because I just remove a random string, but you can do it for yourself if you want to remove, for example, a certain library. You don't want to see its output, so you can just do grep-v and then it will be gone. Okay, so we saw how it works. I think we've come to the reference part. So the flame graph tool is built by Brendan Gregg. It's really nice. He just built it himself, I think in Netflix. And you can use it for all types of things. Like you can start doing profiler. You can just create this output and then you'll see it in whatever you want to profile, right? Julia Evans had a really nice blog post about Ruby and Python profile, which inspired this talk. And, which is also pretty interesting, Nihilus, which is a San Francisco company, just implemented their own performance monitoring service, just a simple script. And they're using it for all the production environment. We're using it, my company, we're using New Relic, which is really nice, but it has some problem, for example, keeping the data, for how long it keeps our data, I think 2 weeks or stuff like that. And you need to pay for everything if you want to get more, right? And you have Python profilers docs, and this doc can be found at GitHub. Okay, thank you. Any questions?
Time for questions. We have 5 minutes. If you have a question, please line up at the microphone over there. Don't be shy.
Feel free. if everything was very clear, it's also okay. So it's also good.
All right, one question.
Yes.
Excellent. Very good. Very good.
Thank you.
So let's talk text. How would you profile your profiler overhead?
Whoa, it's very meta. How you profile your profiler? Actually, you do see the profiler code in your profiling.
Mm-hmm.
It's pretty funny. We might be able to see it here as well. That's pretty fun. Here, you see? Here we can see the extract stack. That's what we use. So it does show up in our profiling. How would you profile it? I don't know. You can see it as part of the profiler, right? Part of the profile output. And I think you probably want to keep it out. So you probably do grep-v and kick it out of your profiling. Okay, thanks.
Well, I will have a question. I will not let you off the hook so easily. And so I really like the talk. What about, I don't know, profiling a multi-processing type of thing with, multiple processes and things?
Yeah. So what Nihilist did, that's how they do. They do it for their real workload. So they have another service which takes all the outputs of the different processes separately, and then merge them in together, and then you can see like across your whole system, your whole processes, whether time is being spent. So you just need to create another service for it. They just created a web server, another web server. Okay, thanks.
When's the next